Thermodynamics. What is thermodynamics? It's basically trying to tell you if a reaction wants to occur based on the energy going in or out of it. There's different components. There's enthalpy, which is dealing with energy per mole. There's entropy, which deals with how much disorder a reaction has. So the more disorder, the better it is, and the more positive the entropy. And there's free energy, which considers both the enthalpy, the entropy, and the temperature. And combined, it tells you if a reaction overall wants to happen. So there's multiple facets to it. We're going to start with this thermochemistry, which deals with reactions in solution. So these are when you're mixing two chemicals together and you either absorb energy or release energy. So that's called thermochemistry. And the concepts related to it are heat and enthalpy. Those are the two primary ones we're going to talk about first. Then we'll start talking about entropy and free energy as we go. So first thing we want to do is look at a chemical bond. So most people realize that in order to break a bond, you need to put energy in, right? It's not something that's free. The thing that people usually don't understand is that when you are actually forming a bond, you release energy. And that's the really interesting thing. So bond making releases energy. It's exothermic, which is basically trying to tell you that energy is exiting the system. So you get a negative value, negative heat, negative enthalpy. But when you break a bond, it always requires energy, always, without fail. So you always have to put energy in to break a bond. But when you form it, you release energy. Which kind of makes sense, right? They're opposite. So they should have opposite values in terms of signs. One should be positive, one should be negative. But for whatever reason, the idea of forming a bond, releasing energy really throws people off. So that's one thing you really always want to remember. That's always going to be an exothermic reaction. And breaking a bond is always endothermic. So units you need to be familiar with. There's two units that are going to be common, joules and calories. The relationship between joules and calories is 1 calorie equals 4.18 joules per, well, there's no per in this part. It just equals 4.8 joules. So when you're trying to do a conversion between calories and joules, this is what you use. So if you're doing a T-chart, for example, let's say you have 100 calories and you're trying to go to joules, then you know that there's 4.18 joules for every 1 calorie. So calories go away. That verifies you set it up correctly, and you're left with 418 joules. Notice I intentionally left over the 0.004 part of it because it's not really important, but if you want to add it, you just put 0.4 at the end, but it's not necessary. So that's a relationship you need to know, the one between calories and joules. This number is actually also what represents specific capacity of water. It turns out the specific capacity of water is 4.18 joules per grams degrees Celsius. So by knowing 4.18, you have two different factors you need to memorize anyways, but same value, so it makes it easier. All right, so let's take a look at a energy diagram. So an energy diagram is basically trying to show you is the energy input or output as a result of a reaction. So potential energy versus reaction progress. So as this reaction progresses, you are putting energy in. When we talk about kinetics later, this is called the activation energy. This energy you need to put in to activate the reaction. For now, let's just look at it as the energy you have to put in. We'll go into the activation energy part at a later date. So because the energy at the required versus what you start with, so you see there's a difference of energy, right? This energy is higher than this. In order to get from here to here, you have to put energy in. This is called an endothermic reaction. So we're going to ignore the first hump altogether. It's irrelevant to us. What we want to do is compare the reactant line versus the product line. The product line is higher than the reactant. You get to put energy in, so it's endothermic, just an endothermic reaction. Same respects, if you go the other way, ignoring the activation energy again, so you see how this is the beginning energy, this is the ending energy. Because this is lower, you're losing energy to get to it. This is called an exothermic reaction. So that's how you could tell endothermic versus exothermic by just looking at an energy diagram. And these are very common, so it's good to get comfortable using them. All right, the other thing we're going to talk about is heat capacity and specific capacity. What are they? They're pretty much the same thing. They're both dealing with the amount of energy you need to make the temperature of a substance go up by 1 degree Celsius. The only difference is that heat capacity is mass specific. So the more of something you have, the greater the heat capacity you have, the less heat capacity. Specific heat is going to be identical no matter how much of a substance you have. And the reason is, For specific heat, we're only looking at 1 gram of substance at a time. So even if you have 1,000 grams versus 50 grams, it doesn't matter. We're only going to look at 1 gram. So, imagine this being 1,000 grams, imagine this being 50. For both of these, we're only going to look at 1 gram at a time. So as a result, the value is going to be identical. So, because the amount of energy you need to make 1 gram of the same substance is the same thing. These are not two different substances. You need to put the same energy into both of them, there's only 1 gram of it, to make its temperature go up by 1 degree Celsius. So specific heat capacity is very important because of the unique value. We can use it to identify chemicals, and they vary based on the substance. So metals have very low values. Water has a very high value, and that's important because it indicates some of its properties. So let's take a look at some of these values. This is joule per gram degree Celsius, kilogram per degree Celsius, which is not the most common way you see it. You usually see it joules per gram degree Celsius, which if you're wondering how do you convert it over, just move the decimal point 3 times to the left, and you get joules per gram degree Celsius. Substances with a lower specific heat have a larger change in temperature, and that's the most important thing to remember. So if I put the same energy into copper, let's say 1,000 joules, and I put the same energy into lead, 1,000 joules, guess which one's going to have a greater change in temperature? The answer is the lead. And the reason for that is because it has a lower specific heat capacity. You need to put less heat to make its temperature go up. The lower the specific heat capacity, the higher the change in temperature. Notice I put the same heat in both of them. This experiences a different change in temperature than this one. The reason this is really important is what if you add a piece of metal, let's say, we'll take that copper, Cu, and we drop into water. Let's say this is 100 degrees Celsius, and we drop into water that has specific heat capacity of 4.8 joules per gram degree Celsius, and copper was 0.387 joules per gram. 0.387 joules per gram degree Celsius. So we drop into water that's at 20 degrees Celsius. Here's what will happen. Water will go up to 25 degrees Celsius. Result of this, the copper, on the other hand, will go down to 25 degrees Celsius as well, because the final temperature for both after equalization has to be identical. So this dropped 75 degrees Celsius. This only went up 5 degrees Celsius. Notice the difference in change in temperature? That's a big, important concept, and here's why. They're going to ask you, if you add this chemical or this substance to water, what's going to be the energy for the two of them? And a lot of people will assume that, oh, because this has a greater change in temperature, the energy is different. No. Never different. Whenever you put a substance into a closed system like they usually will give you, you will assume there is no heat loss to the surroundings, which in English means that whatever heat leaves the copper has to go to the water. So the energy lost by the copper, let's say it's 1,000 joules, will be the same energy gained by the water, which will be 1,000 joules. So the question is, why the heck is there such a difference change in temperature? Specific heat capacities. Look at the difference. For each 0.387 you put in, you make it go up 1 degree Celsius. For each 4.18 you put in, you make it go up 1 degree Celsius. That's about a 10-factor difference in how much energy you have to put in to make it go up by 1 degree Celsius. That's the difference for it. So whenever you're putting a substance in a water or anything else, you're going to assume the energy exchange is going to be identical. Extremely important. Common trick question. The energy is going to be identical, but the change in temperature is going to be different. And the reason they're going to be different is because of different specific heat capacities. And which one's going to have a greater change in temperature? That's right, the one that has the lowest specific heat capacity. So what we're going to say is a low specific heat equals greater change in temp. So remember that. And by the way, this is why you use iron for cooking, for those of you who ever cook. Low specific capacity, and some of you guys will look at these other substances and say, well, can we use these? The lower it is, the better it is, because it heats up faster, right? And you want something to heat up faster because you're using less energy, so less cost. Some of you guys may be like, well, wait, lead is lower than that. Let's use lead. Then you remember, oh, lead poisoning. Yeah, you can die from that. So no, you don't want to use lead. But the lower specific capacity, the better. And gold, awesome, would be great to use, but do you really want to have a pot that costs more than your house? Probably not. All right, so let's move on. So heat calculations. Here's your best friend for heat calculations. Q equals MCAT. MCAT being the test you take to get into medical school, so there's a connection there. So what is MCAT? M is your mass of solution. So remember, your solution has two components, your solute and your solvent. So you have to add. So this is relevant if you're adding a chemical to water. Whenever you add a chemical to water, you have to add the mass of the two of them to get there, the chemical and the water, to get your mass. This is not the mass of the water by itself. This is not the mass of the chemical by itself. It's the mass of the two of them together. Don't forget that. See the specific heat capacity, which is usually going to be 4.18, because predominantly we're going to use water as our solvent. The C is based on the solvent, which 99.9% of the time will be 4.18. Pretty much every time for our purposes. I mean, if you go into college and you do more cool experiments, then maybe not. Change in temperature is final minus initial. Please don't do big minus small number. It's whatever your final is minus whatever your initial. So you can have a negative value. That's important. You can have a positive value. That's important as well. So this is how you calculate the Q. What if you don't have a chemical plus water? It's just water by itself. It's just the mass of the water. Pretty simple. So for water, you're either cooling it down by adding cool water or ice cubes, or you're heating it up by putting it on a hot plate. So it's getting its energy from a different venue. Whereas a chemical reaction, which is basically through it. So what this is telling you is negative Q of water equals Q of the reaction. So which English this means they're opposite signs. Whatever heat is lost by the chemical is gained by the water. Whatever is gained by the water is lost by the chemical. Why is this important? When you do this experiment, all your data is from the point of view of the water. All of your data is from the point of view of the water. So your Q is actually of the water. Bad news is if you're doing a chemical plus water, we really don't care about the water. We care about the chemical because that is considered a system. So in this situation, it's just water. So water is your system. But if I add NaCl to this, NaCl trumps water. It becomes the system. And the water becomes the surroundings. So when we do this calculation, what we have to remember is, let's say we get 1,000 joules when we do the math. I seem to like 1,000 joules a lot because it's very common. That's the Q of the water. So that means the water is gaining energy, right? Because it's a positive number. The Q of the chemical then will be the opposite of that, which is going to be negative 1,000 joules. Why? Because this had to have lost energy to the water to make the temperature of water go up. How did the water go up? You had a chemical to the water and boom, somehow the energy is being input in there. From where? I mean, it has to go from somewhere, right? It's from the chemical. The chemical is losing it. So from the chemical's point of view, it's exothermic. It is losing energy. And guess what? This is the one we care about. We do not care about this. Unless it's water by itself, which is not very common. All right, moving on. So what is the heat of a reaction where 50 grams of calcium chloride is added to 150 grams of water and the temperature is increased from 20 to 25? There's a lot going on. So first off, this is our solute, right? Whatever you have less of is your solute. Whatever you have more of is your solvent. So what I'm going to do is add those two together to get my total mass, which is going to be 200, right? Whenever you have chemical plus water, you have to add the masses. Your temperature, this is Ti, this is Tf. Here's where common sense is going to start coming in, and this is very important. Whenever your temperature goes up, it's always going to be exothermic. Whenever it's exothermic, temperature increases. And guess what? It's going to feel warm when you touch it. So anytime you touch a reaction from the outside and you feel some warmth, it's going to be exothermic, and which means in turn the temperature is going up. And your value for Q is going to be negative. Please remember this relationship. Anytime the reaction is exothermic, temperature is going up, feels warm, negative Q. You could connect it any way that you want. So if you know it felt warm, that means you assume your Q is negative, your temperature went up, and you're exothermic. It's all connected. Once one of these variables is correct, all of them are correct. And that's important because that's going to save you a lot of headache. Because when you do the math on this, the most common brain fart is you do the math, you can get a positive number, you're like, oh, it's endothermic. That makes no sense because you forgot you're calculating the Q of the water, not the chemical right now. Whenever you do a reaction in water, you're always calculating the Q of the water, not the chemical first, because all the data is from pointing to the water. You have more water, so that's where all the data comes from. So on the flip side of this, endothermic means temperature is decreasing, which means it feels cold, which means your Q is positive. So all these are connected again. So if the temperature went down, automatically like, oh, okay, this is going to be endothermic. End again. Don't think. The most common thing is you get really confused because you're like, hey, if it feels cold, why is that endothermic? I mean, don't overanalyze this. Keep it simple, guys. If it feels cold, it's endothermic automatically, without fail. Always. Not sometimes, always. If your Q is positive, it's going to be endothermic and your temperature is going to go down. Just remember this relationship. So before I even start, I know this is exothermic because the temperature went up. So I know it's going to feel warm. I know my Q is negative. I have all this data already floating in my head. When you make that relationship, this becomes easier. So calculating your Q, plugging your value, 200, 4.18, because it's water, right? So the capacity of water. Time to change in temperature, 25 minus 20, which is 5, gives you 4180. Now, if you had stopped there, you would have been wrong, right? Because a positive number, that contradicts reality. How is the temperature going up and it's endothermic? That makes no sense. So that's where the brain fart comes in, right? So how do you avoid the brain fart? Think before you answer. Before you even answer, just put, oh, exothermic, negative. That way, if you forget, you have a reminder, and your value becomes negative 4180, and that's the actual answer. So if you put 4180 without the negative, you are wrong. So please don't do that. All right, ways heat gets transferred. You have conduction, convection, radiation. This little diagram shows everything. Conduction requires direct touch. When you touch something, so two solids touching, your hand touching something else, those are all conduction. You touch somebody's hand, you're hotter than they are, that's conduction, right? Transfer of energy, direct contact, direct physical contact of two solids. That's conduction. Convection can be gases transferring energy. Like if you go out on a hot day and you're like, holy cow, what just happened to me? It's the air molecules that are hitting your body. That's convection, right? That's not conduction. That's not solid to solid. It's gas to you, which obviously is convection. Also liquids transferring energy between themselves. That's convection. Radiation requires no touch whatsoever. This is like sunlight. This is nuclear energy. Things that do not require medium to travel through. Convection requires you to have a gas or a liquid as the medium that energy is transferred through, right? The molecules inside there move and they transfer energy to you. Conduction requires direct contact. Once again, contact, right? Radiation, no contact necessary. So this heat emanating from this hot plate in all multiple directions, that's radiation. It is also conduction when you put the pot on there, right? So there's multiple things going on. So that's the difference between the different ways heat gets transferred. All right, that takes us to enthalpy. So Q is heat. What is enthalpy? Heat per mole. So your old friend, the mole, is coming back to play with you. So how do you calculate it? Most important formula in the whole section. Because if you get a question wrong or you have no idea what you're doing, this is probably the formula you should have used, like 99% of the time. It's kind of like molar mass equals grams per mole. The most important formula in stoichiometry, really simple formula, but people forget to use it, and that messes up everything. This is very important. Look for it. When the question asks you for heat, look at this as a possibility. You only have two options for heat. You either have Q equals MCAT, or you have Q equals change in H times moles. For those looking at this thing, how do I know which one to use which? Well, a couple of different ways. First off, change in temperature, MCAT all the way, no doubt about it. If they give you grams or moles, this is your best friend. If they give you enthalpy, this is still your best friend. So important to remember this one. So let's try a question for it. What is enthalpy in kilojoules per mole when 117 grams of sodium chloride is dissolved in 183 grams of water and the temperature of the solution is increased by 2 degrees Celsius? So if you have two chemicals, your mole value can be for either one. Stoichiometrically, it should work. It shouldn't matter which chemical you use. So you would take either chemical, go to moles, and then take your Q divided by that moles. Here we have water and a chemical. We don't have two chemicals, just have water and a chemical. So our enthalpy is going to be per mole of sodium chloride. So we need to get moles of sodium chloride at some point. So here's our MCAT formula. we're going to get our heat first because we need heat before we can do enthalpy, because enthalpy is Q over moles. This is for laboratory situations. So be clear, so you figure out the heat in an experiment, right? That's the thing with heat. It's usually experimentally figured out. And you get your enthalpy by dividing by the moles of chemical you used. So Q of chemical equals negative Q of water. Remember that. So we're going to flip the sign, get the right value. Remember, temperature went up. Exothermic, going to feel warm when you touch it. All these things are floating in your head. Very important. So negative 2508 joules. Now, what I'm going to do is convert to kilojoules. Why? The most common unit is kilojoules per mole, and they ask you for kilojoules per mole. That's the main reason. In reality, you want to stick with joules as often as possible, because you're going to find out later that most of the brain farts for this section occur because students mess up with the units. If you keep it in joules throughout, you avoid that. Unless they ask for it here, in which case you have no choice but to go kilojoules per mole, but usually they don't ask. If they don't ask, stick with joules. It'll save you a lot of headache. Even if they ask, go to kilojoules and then have another value in joules ready to go for the next parts, because you will see why it's relevant. So negative 2.508 kilojoules as your value. All I did was divide by 1,000. You could also move the decimal point 3 times to the left if you don't want to do the math. Now I need to get moles of sodium chloride. So 58.5, 170 grams, 2 moles. Remember, if there's two chemicals, you could figure out the moles of either one. It will be fine. But if you don't have this as an option, then you do this. Now, in the event you have a balanced equation where the ratios are not 1 to 1, it's like 2 of 1, 1. Go with the one with 1 mole. It'll save you a lot of headache with the math later. So in the event there's two chemicals, and if one of them has 1 as the coefficient, one has 2, go with the 1 as the one you're going to go to moles and divide the Q by that mole value. Here it's NaCl. I don't have a balanced equation because I don't need it, but just keep that in the back of your head. It'll save you some headache later. So all we have to do is divide by these values, and there you go. There's your enthalpy, negative 1.25 kilojoules per mole. The only difference between this and heat, this is per mole. That's it. Why do we do this? Because in order to figure out free energy, you need enthalpy, not heat. That's why. So it's important distinction. Heat is Q. There's two ways to figure out Q, right? MCAT and change in H times moles. Enthalpy has got a whole plethora of options how to figure out. This is one of them. This is not the only one. But you need this to do the other stuff for thermo. All right, so when combustion of 100 grams of methane, how much heat would be generated? It's a heat question. Geez, I wonder what my options are. The most important thing in this section is to first figure out what your formula options are. For heat, there's only two. If you remember that, you will save such a huge headache for yourself. There are only two ways to figure out heat. Just ingrain that into your head. There's only two ways to figure out heat. There is no other ways. What are those ways? Well, you have Q equals MCAT, right? Or Q equals change in H times moles. So which one do I use here? Do you see a change in temperature? I don't either. So we're not going to be able to go to the MCAT route. Now it tells you to write the chemical reaction. Why? There's a little trick that they're going to try to get you on, and I'll show you what that trick looks like. So negative 890.4 kilojoules per mole. So here's the thing you need to understand about this. This is per mole of CH4 and per 2 moles of O2. There's where the sneaky part comes in. Coefficients become players in this equation or calculation. And guess what they love doing? They love giving you ones with coefficients. Why? Because they want to mess with you. So they're ready to do. So in this situation, I'm doing 100 grams of methane. So I don't really care about the 2 part, because if they give me oxygen, then yes, I have to do more work because the math can be a little different. But for methane, good news. I have to do Q equals change in H times moles. Go to moles by dividing by the molar mass. And then there's my heat. Negative 5570 kilojoules of heat produced. Just multiply. 6.25 times negative 890, 5570, negative 5570 kilojoules. That's an exothermic reaction. Combustion reactions are always exothermic. Whenever you're burning something, it's always going to be exothermic. Please remember that. It'll save you a lot of headache later in life. All right, so what if they're asking you for the heat of oxygen? This is where it gets fun, because now you got to pay attention to the coefficient. So you're going to still do the same math. Go to moles, you get 2 moles, right? 64 divided by 32, not a big deal. Here's the tricky part. You're going to have to do this enthalpy, which you did before, per 1 mole of CH4, you have to factor in whatever the coefficient is. So when you're doing the enthalpy, the per mole part is based on the coefficient of that chemical. So if I'm doing oxygen, yes, I have to put 2 moles. What if you don't? Your answer is wrong, obviously, right? Because it's supposed to be 2 moles, but you said, no, it's 1 mole. I'm just going to create my own calculation. Don't do that. So when you do the math, you get negative 890.4, 2 moles, these both go away. So your energy becomes not per mole, that's a mistake, should be just negative 890.4 kilojoules of heat is produced. If you did 1 mole, you would have had double that in the wrong answer. So that's where they're going to trick you. So when they do this calculation for change in H times moles, please remember the coefficient is what you put at the bottom of this. So per mole depends on the chemical. Whatever the coefficient is for that chemical, that's the per mole part you put. So 2, 4, 6, whatever it is. All right, enthalpy of formation. This is the energy you need to form a compound. So this comes into play with, what if you don't have laboratory data for something? Or what if the lab is so expensive or so dangerous you can't do it? In those situations, we see the formation data. So these are calculations for different compounds. So it'll give you the enthalpies for different compounds, and what you're supposed to do is use an equation and solve for the enthalpy of a reaction. It sounds really confusing, but it's not. So the first thing you have to understand about enthalpy of formation, it's based on the elements that make up the compound. So for this reaction, H2O, all you have to do is put the elemental states of the elements that make it up, H2 and O2. Why is it half? Because you want to have 1 mole of the product always. So I'll give you a comparison. Let's say we're doing CH4. So I'm doing the enthalpy of formation reaction for it. How do I do it? So elemental form of carbon is just C. What's the elemental form of hydrogen? Well, you might have to remember your diatomics, right? Hofbrinkel, your old friend. These always exist in pairs. This is where it comes into play. So H2 will be what you need to use, right? So if you put H, you'd make a mistake. Now this one's fine, so all I have to do is put a 2 here, and then there's the enthalpy. This is the formation reaction for CH4. If I'm doing CO2, on the other hand, what's the elements that make up CO2? C plus O2. Really simple, nothing cute going on. What cute happens is like this reaction. So let's look what it was originally before I modified it. So if you're doing formation reactions, and these are very common, you do have to understand how to do them. Just look at the compound. What elements make up the compound? Hydrogen and oxygen. So H2, the elemental form of hydrogen, the way it's found in nature. And for oxygen, O2, right? So if I balance this, I'm going to put a 2 here, right? I'm going to put a 2 here. Here's the problem. When you do formation reactions, it could only be based on 1 mole. So what I want you to do when you do a formation reaction, do like this, balance it like you usually do, and at the end, divide everything by whatever the coefficient is in front of the product. So divide this by 2, divide this by 2, divide this by 2, and that's how I end up with H2, one of these, right? Half O2 plus, which produces H2O. That's how you do it. And just to give you one other example, let's say we're trying to do sodium oxide. We're like, oh, what's the formation reaction for it? Na, elemental form of sodium, right? There's no diatomics involved, nothing cute, plus O2. So balance it, put a 2 here, which means you have to put a 4 here. And you look and say, wait a second, can't have a 2 here. So divide everything by 2. There's the half again, because half is popular in 2. So 2 plus 1/2 O2 produces 2 Na2O. So that's your deformation reactions. Just look at the compound, what elements are needed to make that compound. The only thing you got to watch out for is diatomics. Those are the ones that get cute, right? The H2, the F2, that kind of stuff. The rest of the elements, just put the element by itself. If it's CH4, just carbon C. What if you have, let's see, NH3, N2 and H2? What if you have sodium fluoride, Na plus F2? So the diatomics is where it gets interesting, but as long as you follow, this should be fine. The enthalpy of formation for chemicals in elemental state are 0. So the enthalpy of formation for O2, F2, N2, all these diatomics are all 0. What's the enthalpy of formation of Na? 0. Why is it 0? It's already there. You don't form it. Enthalpy of formations are only for compounds not naturally found. Some of you guys may look at O2 and like, that's a compound. No, it's technically an element. And it's in the normal form, so you don't do anything cute with it. So it's going to be 0. So anything an element to form, the heat of formation is enthalpy of formation going to be 0 for it. Values for it is used in the following formulas. So here's your friend for all this. You're going to use this formula to get the enthalpy of a reaction. So by knowing the enthalpy of formation of the chemicals, the compounds in the reaction, you can figure out the enthalpy for the overall reaction. So how do we do this? Well, let's take a look. Write the elements in the compound on the reactant side and balance it. Divide the coefficients for all the chemicals in the. So this is basically showing the enthalpy of formation again. So I guess I want to walk you through it twice. Let's just do it real quick. So reaction showing the formation of ammonia. So NH3, remember, N2 and H2, because those are the elements that make up the compound. And then what do? Divide everything by 2. Why? Because this has to be 1. Has to always be 1. Always. Not sometimes, always. So you divide everything by 2. That's how you get half and 3 halves. And then 1 NH3. So that's how you do another enthalpy of formation reaction. So hopefully after all this, you have a better idea. All right, so calculate enthalpy for the following reaction. So we have a compound. I want to know the enthalpy for this overall reaction. How much energy per mole is this whole reaction producing? That's where enthalpy comes in. It looks at the reaction, gives me the enthalpy for the overall reaction. So how do I do this? I don't want to do Q equals MCAT. No way. Too many things going on. So what I use instead is enthalpy of formation data. So this would have a value. It's a compound. This would have a value. It's a compound. This would be 0. This would be 0. Elementals for both of them. That's why they're listed as zeros. Products minus reactant. You multiply the coefficient times the chemical. So there's your equation. And what I would like you to do is always do this part. Without any numbers, just put the coefficient times the enthalpy of formation, set up like this. So 1 times enthalpy of formation of Al2O3 minus 1 times this. So just put the coefficient times whatever, just put triangle HF, the chemical, for each one of the chemicals you need to use. Why do you do this? To avoid brain farts with the math. So just make it a habit. If I don't see this, you're not going to get any credit for the answer. So you need to do it. So the reason that you want to do brackets also, pay attention to this. Whenever you do products minus reactants, always have your reactants whole thing in brackets. You can do the math inside the brackets and then deal with the sign. This sign thing screws people up royally. So avoid that. Because people forget that negative times negative makes a positive. So this value becomes negative 850, not 24, 26, whatever it's going to be, 24, 25 something. So that's where the brain farts come in. Signs and units are big brain farts. So negative 850 kilojoules per mole, because this is enthalpy, this is not heat. Heat is always going to be just energy. And that's the other thing I want to point out. If you ever see calories or joules without per mole, those are your Qs. Just look at them as your Qs. And they say energy is, or those are all Qs. That's Q. When they give you per mole, assume it's your enthalpy. That's the distinction. Why is it so important? Well, if they're asking you for enthalpy and they give you energy, you have Q. Q per mole gives you enthalpy. So it helps you avoid some brain farts. Here's another question. So O2, we know it's going to be 0, right? Any other elements? Nope. So this is going to have a value. This is going to have a value. This is going to have a value. So we want to figure out the enthalpy using the enthalpy of formation for the following chemicals. So I have enthalpy of formation of H2O, have it for CO2, and have it for CH3OH. Products add together minus reactants. So what am I going to do? Remember what I told you guys. Always write this out just like this. I don't need the overall equation of summation form. I don't need that. But please do this. 2 times enthalpy of formation of CO2 plus 4 times enthalpy of formation of H2O. And I should have put brackets here, so my apologies for that. Minus the enthalpy of formation of CH3OH. So now we're going to plug in our numbers. So 2 times negative 394 plus 4 times negative 286 minus 286. I'm just going to put this whole thing in brackets. We'll deal with this last. So then once you multiply these together and add them, it's going to be minus a minus, right? Which is like what, 478. So positive 478 plus whatever you get on the left side from these numbers, from the products, you'll get negative 1454 kilojoules, and once again per mole, because it's enthalpy. No, I'm forgetting the per mole part. All right. That's one way of figuring out enthalpy. So you figure out, we saw the Q over moles. That's one option. There's the enthalpy of formation. So enthalpy of formation is that reaction, that equation every time. What if we don't have enthalpy of formation? What if we don't have anything related to Q? What do we do? Well, there's a third option, and that's going to be your Hess's law. Hess's law is basically this thing. What it does, it gives you multiple reactions, just like this. So anytime you see multiple reactions and ask you for enthalpy for a different one, it's Hess's law. How do you do this? Okay, this is where it gets really interesting. It's a mental game. It's like a puzzle. What I'd like you to do, look at the final reaction. Your job is to make these three look like this at the end. I know what you're saying. How the heck would I do that? Here's the trick to it. Pick a chemical that's unique in the reaction, meaning that it's the only source. Like if I look at this, N2 is not even in the final reaction, so I don't care about N2. O2, not in the final, I don't care. NO, it's in the final reaction. Is this the only source of NO? No, I also have it here, right? So I'm going to skip that reaction altogether. Why am I skipping it? Because if you try to deal with it now, you may make the wrong decision. So we're just going to leave it alone for now when we come back to it. So we're going to look at the second reaction. All right, NO is still there, but we have one other chemical. We have NO2. Is this the only source of NO2? Do you see any other N2? No, you don't. It's unique. So we're going to deal with it now. Whenever a chemical is unique, means the only source out of all the reactions given, this is the only place where that chemical exists. So what we need to do is put this in the correct side. So we're going to put on the left side, right? Because it needs to be on the left side. So I'm going to flip it. And when I flip it, this number is going to be going from a negative to a positive. When you flip a reaction, the sign flips with it. That's point one. Just visualize it for a second. We'll get into the specifics of it in a second. I just want to make sure you understand the big picture. Once I flip it, you see how the coefficient's 2? What's the coefficient for this? 1, right? Guess what I need to do? Divide everything here by 2. Divide this by 2, this by 2, this by 2, and this by 2 as well. Everything's divided by 2. Why? Because you have to make sure NO2 has the correct coefficient. So because it's the only source, once I flip it, I need to make sure I have it as well, because I want to make sure I only have one NO2, not the 2 they're giving me. I know this is going to sound scary, but don't worry, it gets better. Then the third reaction, is there anything unique? N2O, is there any other source of NO2O? N2O on here? No, only source. Okay, so because it's the only source, I don't need to flip it, because N2O has to be on the left side. But looky there, there's only one of them here, but here it's showing 2, so guess what I have to do? Divide everything here by 2, including this. So that takes us to the first reaction. What do? Do we keep it or flip it? Well, now that we flip the second reaction, so the second reaction, just to show you what it looks like now. So you have NO2 produces NO, because we divided it by 2, right? Plus 1/2 O2. So that's what this one's gone. And this is going to be negative 113 divided by 2 kilojoules. We're not going to worry about the math right now. Okay, so NO is on the right side. You see how NO is supposed to be on the right side? So now we look back at the first reaction we didn't touch. Here's where I was smart, we didn't touch it. Where does NO have to be in order to give us a total of 3? Well, we already have 1, right? If we add it with this one, that gives us 3 total. So all we have to do is keep this reaction as is. Don't divide, don't multiply, don't flip, nothing. Keep it, you're good to go. All right, so now that you see the big picture, let's deal with it in parts. So here's what you're looking at. So first reaction, keep as is, since NO is on the product side. And originally, remember I told you, skip it because of what we said later, but keep that in mind. Flip the second reaction, so NO2 needs to be on the reactant side. This final reaction has only one NO2, you divide this reaction by 2. So you notice what happens? You get NO2 produces NO plus 1/2 O2. Divide the value by 2, you get your answer. Third reaction is kept as is, so you see N2 on the reactant side, but you need to divide by 2 to get the correct numbers. So you saw how when we flip it, the sign flips. When we divide it, we divide the energy by the same value. If we multiply it, hypothetically, we'll multiply it by that value. Whatever you do to one thing, you have to do to everything in the reaction. So once we do all this, we get this thing. So with this thing, notice what happens. So you have N2, Anything on opposite side, subtract out. So 1 and 2 here, 1 and 2 here, bye-bye. They both go away. 1 minus 1 is 0. O2, 1 here, half and a half. What's half plus half? 1. 1, goodbye. They're both gone. What if there was only a half here? What if it was 1 here and half here? Then you'd be left with a half on this side. So it'd be half O2 on the left, just in case you're wondering what happens. Anything else we cancel? No. So now we need to bring everything down. We bring these two down, just like this. We bring the products down. Now, if it looks like the final reaction that they gave you, you did it well. Good job. Then all you have to do is just add these numbers to get add. So I know what you're saying. Well, this is a negative. Yeah, add it, but you're basically subtracting mathematically, right? The reason I don't want to tell you subtract is because if you do plus plus minus to minus, then you get a positive number. Don't do that to yourself. Just add all the numbers and just put in a negative sign in your calculator as you do it. Problem solved. So this is the energy per mole. I don't know why I keep on forgetting per mole for this reaction. So this reaction is an endothermic reaction that requires 155.6 kilojoules per mole of energy in order to occur. Pretty complicated, I know, but when you do a few of these, it's a game. It's a puzzle. Just make sure you do what I told you to. Find whatever's unique in the reaction, put in the correct location, and go from there. All right, spontaneity. So now we're going to be talking about if a reaction is spontaneous. What is spontaneous? It happens by itself. You don't need to do anything, it happens. That's what spontaneous means. So when you release the stopcock right here in the middle, the two gases mix. They equally mix. That's spontaneous. If I were to try to make these two end up on one side by themselves, that is darn near impossible. That is non-spontaneous. So if a reaction is spontaneous in one direction, it's non-spontaneous in the other. The first thing we're going to talk about is entropy. Measure the amount of order of a reaction. The more disorder, the more positive entropy. So positive entropy is a good thing. So disorder, chaos is a good thing. An excuse you can make when your room's a mess. Just say it's the way of the universe. I'm trying to not fight the universe. Disorder is the way everything exists. I need to go along with the world. Now, good luck with that. But you can actually mathematically explain if you think about it, right? You can just put entropy down, say, look, this is the entropy of my room. It's going toward more chaos and disorder. It's a good thing. I'm trying to teach you thermodynamics, right? Tell your parents that. See how it goes. So more order is not good. Order is bad. Disorder is good. If you're creating more order, you have a negative entropy. So if I'm trying to go from a liquid, pretty chaotic, to a solid, pretty organized, I'm going toward order, right? Because the solid is more organized. It's more order. That's negative. That's a negative entropy. So when you're changing states, you can actually figure out the entropy for each one just by knowing the state change. So on the flip side, if I'm going from liquid to gas, my entropy goes up, right? I'm going toward more disorder because the gas is more disordered than a liquid is. So keep that in mind. So positive entropy whenever there's disorder can also be determined using a balanced chemical equation. How do you do that? If you have less moles of gas on the product side, the entropy is negative. If more moles on the product side, entropy is positive. So all you have to do is count your moles of gas on the reactant and product side. Pretty easy. This is when you have no numbers. If they just give you a reaction with no numbers, count your moles of gas. I know some of you guys are like, what if there's no gas? Common sense at that point. What if you're taking a solid and dissolving it in water? You're going from a solid to ions. Is that order or disorder? Disorder. That's chaos, right? So that means entropy goes up in that situation too. So if there's no gas involved, use common sense, guys. Just ask yourself, what's more organized? What's more ordered? And then you'll be able to answer the question if it's positive or negative. So let's take a look at 4 reactions. So the first reaction, we have 1 mole of gas here, plus 2. That gives us a total of 3 moles of gas. And when you're explaining this, you have to say that there are 3 moles of gas on the reactant side. There are 3 moles of gas on the product side. As a result, your entropy is near 0. And that's what it is. Your entropy is basically 0 in this situation because there's no change in entropy. There's no difference in the moles of gas. They do exist like that, just FYI. All right, for the second reaction, we count 1 plus nothing, just 1 mole of gas here, and then 2 moles on the product side. So you would say, and this is how you would verbally explain this, there's 1 mole of gas on the reactant side and 2 moles of gas on the product side. Thus, you're going toward more disorder and entropy increases. That's full credit. That's what you have to say. Just count moles of gas on both sides. Tell them that it's going to more disorder. Tell them entropy goes up. You're done. Simple as that. This reaction, calcium carbonate, notice 0 moles of gas on the side, 1 mole on the product side. So what do I say? There are 0 moles of gas on the reactant side, and there's 1 mole of gas on the product side. As a result, you're going toward more disorder, and the reaction is going to be having a positive entropy. That was too many words. Just say entropy goes up or it's positive. I don't know why I went roundabout there. All right, next reaction. You have a solid dissociating. No gas, right? Common sense. Is this more order or more disorder? Disorder. Ions. They're moving around more freely than a solid ever would. So you would say there's there's a solid on the reactant side and 4 ions on the product side. As a result, you're going to a more disorder. So the entropy is positive. That's how you explain it. All right, what about the math version? So there's actually entropy of chemicals as well. Here's the interesting thing. So you know how there's enthalpy of formation of elements are 0? Not for entropy. Entropy actually has values for elements, so you can't ignore them. I just want to make that clear. So if they give you O2, yes, O2 does have a change in S value. Don't ignore it. Big no-no, entropy of formation value for it. So what do I do mathematically? Your product minus reactant. So basically, you're going to have to have a value for each chemical. You notice the units, joules per mole, Kelvin. Please don't forget that. Remember how I told you enthalpy was usually kilojoules per mole? That's where the brain fart comes in. This is joules, that's kilojoules. At some point, you have to use those two numbers together, and people don't forget to change units. So how do you avoid that? Just go to joules all the time. Makes it easier. So just like last time, I'm going to do products. So you have to show this line. If I don't see this line on your paper, you get 0 credit. So 2 times entropy of formation of HCl3 plus 3 times entropy of formation of H2O. There's my brackets. 1 times this, and then 6 times that. Now we're going to plug in our numbers. So you can't go straight to plugging in numbers. I better see the work first, guys. All right, so there's our numbers. I'm going to do the math. And then, see, this is why it's very important. You have products minus reactants. So I did the math for the reactant separately. I did it for the product separately. And then what did I do? I did the math for them afterwards. So now it's 851 minus 428, which gives you 422.13, which technically has too many sig figs. Let's see how many should we have. 3 in our answer. Should have been 42.1. So 422 exactly, because our least significant value has, which is all the way up here, has 3. So I should have just stuck with 3. I don't know why I put 0.113. All right, so that's how you figure out the entropy. So very similar to enthalpy of formation in terms of how the math works. The only difference is you have entropy data instead of enthalpy data. That takes us to what pretty much is the crux of all this, which is Gibbs free energy. This takes into consideration your enthalpy and your entropy and tells you reaction is spontaneous or not. So whenever they ask you if a reaction is spontaneous, it's a change in G question. Anytime they ask you what the driving force of reaction is, it's a change in G question. So anything to do with whether a reaction wants to happen or not is based on G. Don't forget that. G is the god of all this. This is what determines if a reaction wants to happen or not. So the value determines if a reaction is spontaneous or not by factoring entropy, enthalpy, and temperature. So it's everything considered. Here's your formula. This is your best friend. This formula will be used extensively, so please remember it. Change G equals change in H minus T change in S. Where's the brain fart? H is usually kilojoules per mole. S is usually joules. People forget to convert. Boom, you get nailed. Avoid that. Always being joules. Joules makes you happy. If your G is negative, so rather than say less than 0, let's just break it down. If change in G is negative, reaction is spontaneous. So negative is good. Please don't make it positive. So let's review for a second. Entropy is positive and spontaneous, right? That's a good thing. Negative is bad for entropy. For enthalpy, which one do you think is going to be the favored one? Which type of reaction wants to happen? The one that requires energy or releases energy? That's right, the one that releases energy. So exothermic or a negative enthalpy is good, which means it wants to happen more. And your enthalpy being positive is bad because you have to put energy in. That requires work, right? You don't want to put energy into something to make it happen. So factoring all those in together comes to G, and when your G considers your H, your T, and your S, that's when you tell if a reaction wants to happen or not. So if the G is positive, it's a bad thing. Reaction is a no-go. Will never happen. One other thing I want to point out, If they tell you a reaction occurred, your G is negative automatically. Automatically. Anytime they tell you a reaction has occurred, your mind should be like, oh, G is negative. Doesn't mean I know my S and H are off the bat, but I know my G is negative. Automatically. Don't forget that. And if it's zero, you're at equilibrium, and we'll deal with equilibrium in more detail later. Brain fart alert, make sure your enthalpy and entropy are in joules when doing calculations. It's a brain fart alert, excuse me. So if you have a brain fart like this, you're going to lose a lot of points, and you'll get a lot more work. So avoid the brain fart. All right, so this is how all this is factored in. So please don't memorize this thing. This is all common sense. I just want to show you how this works. Remember how I told you if your H is negative and your S is positive, those are the ideal conditions for a reaction wanting to happen. Guess what? Your G is always negative when that happens. That's why. It makes sense. Regardless of temperature, this reaction will always occur. What if your enthalpy is not favorable? It's positive. Remember, that means you have to put energy in. And your entropy is also negative. Doesn't want to happen. It's going toward order. It's a no-no. This reaction will never occur. Never. You can't do anything. So I know what you're saying. What does that mean? So does that mean they either have or always occur, not occur? No, because there's another variable we're not considering here. Temperature, right? So let's look at the temperature one. So temperature comes into play when they both have the same signs. When they're both negative or both positive, that's when you have to look at temperature more carefully. So your H, well, that's great. Exothermic, that's what we want, right? Energy release, that's a good thing. But your S, really bad. Order. I don't want order. That's a no-no. So what determines if a reaction wants to occur or not? Temperature. If your temperature is low, your TH/S value is going to be smaller, right? Which means your enthalpy will have a bigger role in this calculation. The math will be bigger. So if you have a negative 1,000, and let's say when you multiply these together, we get positive 800, that gives you negative 1,000, gives you 200 overall. Negative 200. That's a good thing. Negative means it wants to happen spontaneous. So that's what we want to look at it. So that's when temperature comes into play. If they're both positive, that's a no-no. That's bad, right? We don't want enthalpy to positive. But this is good. This is disorder. Yay. So what determines this? Temperature again. If temperature is high, that means your TH/S value is going to be more dominant, which means the reaction is going to be more likely to give a negative number. And for those that are kind of confused by that whole thing, it's negative times whatever you have here, right? So what's negative times a positive? So negative for the sign, for the calculation, times a positive S gives you a negative, right? And what do we want our G to be? Negative. So if this number becomes bigger because your temperature is higher, this G becomes more and more negative, and that's more what you want. All right, so use the free energy equation to predict the spontaneity of the melting of ice at 10 degrees Celsius. So here's where common sense comes in. First off, did this reaction occur? Yes, G is negative. Yay! That's how easy it is. Now, what about your S and H? So let's make an argument. Because if they ask you a question like this, you have to talk about all variables, G, S, H, and temperature if necessary. Is this going toward order or disorder? Disorder, right? Solid to liquid. S is positive. What is your H going to be? To melt something, does that require energy or does that release energy? Requires. So your H, change in H is also positive. So now, put your little equation down. Now, you know it occurred because it tells you it happened. So your G is negative for sure, but this is how you would do it. So you put a positive here. Positive times negative gives you negative here. So what determines this reaction? Temperature. So if the temperature is significantly high, the reaction will occur. Well, if the temperature is low, this reaction will not occur. That's the way you want to look at it. So what's the temperature value? That's unimportant. The only thing you need to know is that temperature is the player in this. At high temperatures, you state the reaction is spontaneous, and low it's not. This reaction occurred, so you know this temperature is pretty high, right? And it's 10 degrees. Ice melts at 0, common sense. So it definitely wants to happen. So we could do math to verify it. We're going to do that. So we plug in our H, 6.03. There's our positive. See, before even we calculate it, there's a positive number. See the beauty of doing the math? Notice I converted to joules, so I don't have a brain fart. So now I got to do plug and chug, negative 2. See, we already predicted it. Before even doing the math, we knew whether this reaction was supposed to happen or not. And now you have to be able to do that. I can't stress that enough. You have to be able to do this stuff on top of your head. And this equation is your best friend. You have to use that extensively. So when they ask you for spontaneity, change the G question. Just remember that. Spontaneity, change the G question. Write the formula, figure out your enthalpy and entropy. Because if you don't, you're going to mess up every single time. The other thing they're going to ask you for is what's the driving force for this reaction? What's allowing this to occur? H cannot be the driving force. I know you guys are like, why not? Because if H is the driving force, this reaction is going to always give you a positive change in G. Is that what you want? No. You want a negative change in G. So that's a no-no. That's not the driving force. So what is the driving force? Your entropy is. So your driving force is either your enthalpy or your entropy. How do you determine which one? Which one is determining if the reaction is going to be negative or not? If it's your S is your driving force. It's your H is your driving force. What if they're both what you want? And what if this was negative and this was positive? Your S was positive. That reaction always occurs. So in that situation, both of them are driving forces. But that's what the driving force question is, in case you ever get one. So change in G is negative, so the reaction is spontaneous. So with numbers, without numbers, either way, you can figure out if the reaction wants to happen or not. So calculating change in G, formula options are, here's player number 1. Here's player number 2. So remember that, please. Those two are your options. What's the more common one? The second one. K. Now, we're not going to talk about equilibrium right now, but I'm going to show you how to calculate it because you're going to need to. It's easy. It's E to the negative change in G divided by RT. So E is your E to the exponent on your calculator. So what you're going to do is your E to the exponent. So you're going to take change in G, multiply by negative, flip the sign, right? Divided by RT, and then you're going to press the E to the exponent on your calculator, and it's going to give you the answer. So R is 8.31. Whenever you're talking about energy, this is your R for energy question. This is different than 0.08201, which is for gases. This is for energy. So 8.31 is for energy. Just remember energy. Your temperature has to be in Kelvin, just so you know. Your change in G must be in joules. Why must it be in joules? Because your R is in joules. So what if you put in kilojoules? You just got the wrong answer. How often does this happen? Pretty frequently. I guarantee you one of you is going to do it. Even after I tell you, avoid this, you're still going to do it because it happens. Oh, and your T is in temperature in Kelvin. So that's how you do the calculation. Enthalpy, you have different options. You have Q over moles. That's your best friend. That's your first thing you're going to look for. Just look for Q over moles first. Is it possible? That's the route you're going to take. Option number 2 is your enthalpy of formation. How do you know it's enthalpy of formation is the formula? If you have HF values. If you have HF, this is your friend. Hess's law, how do you know? Multiple reactions. This is a hierarchy. You're going to look for the first one first, then the second one, and then the third one. Do it in that order every single time. If you don't look at it in terms of formula, you're going to screw up on this royally. Please understand, if you want to make this section easy, it's formula based. Once you start looking at things in terms of which formula would this be, this section becomes ridiculously simple. And it's one of the nastier sections in chemistry, just so you know. Physical chemistry is extremely nasty. There's a whole class called PChem, which gives students nightmares, dedicated to thermodynamics. I'm giving you an easy way around that. Just remember what I tell you, and things will be easier. Here's less common, but still possible. Your change G formula can actually be manipulated to solve for H. Those are only 4 options. There is a 5th option, but that's to do with Lewis dots. We'll talk about that later. For now, these are your 4 options. Any question, these are your 4 options. There is no 5th option for us right now. So please don't screw up and look for other things. And if you don't look at a question in terms of this, you're going to screw up. Heat, 2 options. MCAT, whenever temperature is given, and change in H times moles whenever you're given either grams or moles, or a balanced equation, or all 3. And that is enthalpy in a nutshell. So hopefully that makes it a little bit easier. Just remember, it's formula based. If you do it in terms of formulas, this section is a walk in the park. Otherwise, you're going to be walking in the jungle.